Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So we're delighted to have here Danny Vilenchik from, Danny's a PhD student in Tel Aviv University. He's visiting here for 3 weeks. This is his third week. And he'll tell us about why almost all k-colorable graphs are easy.
Okay. So this is a joint work with Amin Korja-Oglan and my PhD advisor, Michael Krivelevich. Okay, so let's start. So the outline of the talk, so I'll start talking about random graphs, phase transitions and clustering, which, judging by the audience, should be like, we can go fast on this. And then we'll talk about how do typical k-colorable graphs look like. I'll show how our result is also applied to message passing algorithms in the SAT setting. And then, depends on how much time we have, I'll go into two proof techniques that we used in this paper. Okay, so the coloring problem. So you're given a graph and you want to find a function f that assigns each vertex a color, a number from 1 to k. And you want the coloring to be proper, that is, every two vertices that share an edge will get a different color. And you want to find such an f with minimal possible k, and such a k is usually called the chromatic number, chi of g, and in this example you see that the chromatic number is 3. You can color it with 3 colors, but not with less. So the coloring, finding a proper k coloring with a minimal k is NP hard, and what's worse is that there's no reasonable approximation for this problem.
FK is who?
Uri Fege and Joe Killian. Unless NP is so ZPP is some kind of complexity class.
And nobody believes that.
So it's a randomized algorithm, polynomial time, expected polynomial time algorithm that has no mistakes. It gives you the right answer. Only its running time, you are not sure it's going to be polynomial, but it's expected polynomial over its.
Yeah, so maybe it's a reasonable assumption.
But not almost, because that's a different class. Okay.
Okay, so having established that the problem is notoriously hard, so one way to proceed is to consider random models and average case analysis. So to this end, let's remind ourselves of the famous GNP model, where every possible edge is included with the same probability. And the expected chromatic number for GNP is rather high. It's basically the average degree, the expected degree. A bit less, but it is comparable with the average degree. So another model that one can consider instead of GNP is GNM, where you choose uniformly at random m edges. So the one benefit of considering GNM rather than GNP is the fact that if you prove that some property holds with high probability over GNM, then you can immediately say that it holds for all graphs with m edges. Whereas in GNP, so GNP is not the uniform distribution over. So it's not uniform, I guess, in any sense, and GNM is uniform over graphs with exactly m edges. So this will come as a technicality maybe later on, but but for most scenarios, GNM and GNP are basically the same. You have this exchange rate between them, but so when the number of edges is the expected one, then the models are close. And so a very well-known phenomena that occurs both in GNM and in GNP is called the k-colorability threshold, which is if you take a random graph in GNM whose average degree is bigger than D. So here I'm slightly cheating. Maybe D depends also on N, and maybe it's not a constant. It's still maybe an open question, but for our purposes, like, it's enough to get the spirit of things. So you have a constant, and if the average degree of the graph is higher than this constant, so almost all such graphs will not be k-colorable. And if the average degree is smaller than this constant, so a typical graph will be k-colorable. And this is Ehud Friedgut. And this is one example of a phase transition. So experimentally, people saw that if you take G and M and you take the average degree to be slightly below the k-colorability threshold, then the distribution is hard. Namely, many simple heuristics that one would think of fail. And one possible explanation that comes from statistical physics is the structure of the solution space or the k-colorings of such graphs. So we are talking about structure and geometrical, so let's just define what do we mean by distance or the geometry of colorings, the space of k-colorings. So we consider two k-colorings to be the same if you just permute the color classes, and one is a permutation of the color classes of the other, then they are the same. And we say that two colorings are a distance t. If they agree in every permutation, they disagree on the color of at least t vertices. And there exists one permutation that obtains equality. So this is the regular Hamming distance that one thinks of. So I'll be using this experimental guy to show, instead of saying repeating that some of the statements are based on non-rigorous analysis, that is, not things that are rigorously proved, maybe solving things with a computer. So this will stand to denote that these claims are not rigorously as we see them proved.
Wait. But what you're going to talk about is rigorous.
Right.
Proved. You're
but
just
I'm
going over the physics stuff.
Right. So I'm comparing it with what's known in other aspects, and there it's not all rigorous. So if you take G and M with an average degree below the threshold, so this is the conjectured picture. So if you consider this all k to the n possible colorings, so you have, so the blue ones are clusters of colorings, and you have many clusters of colorings. So what makes a cluster? So all colorings which are close in Hamming distance will sit in the same cluster, and a linear number of vertices are frozen.
So wait, do they all have to be close, or is it necessary? It's just necessary to find the nearest neighbors?
To find
Well,
out.
but if the thing is small, then you can move from one to the other.
These things are usually. I mean, so what's the definition of close? Is it that
Of a cluster?
any of a
Close.
cluster, any pair of vertices in a cluster or of configuration in a cluster have distance at most 500, or between any two pair you can find a path.
So if you take just the diameter, take the farthest two k colorings. So it should be, I don't know, maybe n over 2000 or so it should be, so they should be close to each other.
And how far are these clusters supposed to be from each other?
From each other? Well, I'm not really into the, so I know this is the picture, but I don't like know the numbers exactly. But the main thing is that the clusters are far, let's say, much farther than the distance between the cluster. And that a linear number of vertices are frozen. That in all k colorings, if you, of course, disregard permutations, they will take the same color. So all these vertices sit in the same color class in all the colorings.
And all the colorings in a single cluster.
Yeah, all the colorings in a single cluster. So there is a linear fraction of the vertices, and they sit together in the same color class, regardless, of course, of its name.
So there are no examples where there is a continuous link between two, I mean, as was asked before, the clusters are separated, but
if you take the degree lower, then it will, of course, conjecturedly, it will become one cluster.
So as you vary, this is G and M, but if you took G and P, as you vary P for P small, they will be continuously connected to each other. There's a certain point beyond which but not yet at the phase transition point. There's a certain point beyond which it busts up into clusters. That's presumably where it's getting harder to simulate it.
And this is all conjecture, right? Nothing of this was rigorously proven.
This is hand wave.
This is the man that I was talking about.
Right,
So
right.
this is all to exactly.
Some of that actually is proven in other models, right?
Right, so
Yeah.
as we also prove rigorous stuff about this thing. So every two clusters are far, and there are exponentially many clusters. So such results were proved just recently rigorously for k-sat, for k greater or equal than 8, and the work is Aklioptas and Ricci, and it's from the last stock, I think. So it was proved rigorously for k-sat and for k equal 3, so maybe this is not exactly the case. Maybe there is also some huge cluster beside the small cluster. So I think these theories keep changing every now and then.
So MMZ is the physics.
Right, it's Mezad, Zekina, and
Monas.
yeah, okay.
No?
Montanari.
Oh, Montanari. Okay.
But much of that paper is also rigorous, the physics paper. This MMZ. Or 5.
This one, yes, because here the rigorously. So this is just to get the flavor of things. It's not just so you will have to compare.
Everything. So is it there? There we know the diameter is a small constant times n or little O of n, or what do we know?
About in these papers, so I didn't read any of them. This is what I would guess also.
Small constant times n, and the clusters are away a large constant.
So what they can prove
Yes.
is that the clusters are away large constant times n, and whether then the question is how do you define a cluster? I think to say what's the diameter of a cluster, because maybe they don't exclude. I think the situation where maybe there are much smaller clusters and they are in some like
Oh,
a
like a
little
hierarchy.
of n diameter clusters, which are together in some. Each one is part by epsilon times n from other clusters. So there can
So
be
a hierarchy.
I don't think the results exclude this possibility. But what they do prove is that there must be satisfying assignments which are close together, and there must be pairs, let's say, satisfying assignments for which there's no satisfying assignment close to it.
So
I mean, beyond. So for some satisfying assignments, you have several satisfying assignments close to it, and nothing in the middle, and then
so
others which are far.
gap, there is no two solutions which have distance 0.5 times n.
That's
Either have
Yes. There are no two that have distance intermediate.
Yeah. So
Okay.
it's not like 0.5, that's 0.3
Yeah,
times n.
But there's
There's
there
0.4
is
and
something.
0.2, but not 0.3.
Yes.
Okay.
Okay, so having said that, so this structure obviously makes life harder for the heuristics because they can get distracted, right? They try, every cluster moves in his direction, maybe they try to find some compromise, and there is nothing in between, as was just said, and the algorithm fails. However, the survey propagation, as claimed, does well on such, so it is supposedly tuned to this clustered energy levels configuration. Okay, so in our work we considered GNM, but with an average degree, which is a constant but above the colorability threshold. So if you just take GNM, it's not suitable to study k-colorable graphs because typically a graph in GNM will not be k-colorable. So instead we consider the most natural thing, which is GNM conditioned on k-colorability. So you just take the uniform distribution over k-colorable graphs with exactly m edges.
So what you're saying is that you're putting yourself in the unsatisfiable.
Regime, but then we're taking
But you're taking like the zero measures.
right the small exponential.
Yeah. I don't mean really zero, but approaching
Right.
zero measures. Okay.
And this is what we consider. So this is like arguably the natural thing to do. You take the uniform distribution, and maybe a less natural thing to do is to consider the planted distribution, which is more approachable and easier to analyze. So what's the planted distribution? Let's think of three colorability. You just partition the vertex set into 3 parts. So here they are of equal size, n over 3, but it is not necessarily so. The analysis will work also if you partition it to other sizes. So you partition it, and then you include m random edges that respect the coloring. So this is where the name comes from, the planted coloring, as you force one coloring to be legal, and then you are guaranteed that the graph is 3 colorable.
So wait, I see. So does it only have one coloring? I mean,
no, because it does. If m is large enough, then the answer is typically yes. But if you take m to be constant, in particular, you will have vertices with degree 0 or degree 1, which are very poorly connected, and you can they induce many colorings. So typically,
but
no.
If you're just above threshold and you have planted, then there's still many.
Right. Yeah. If you're
for any m which is a constant multiple of
Right.
n, you still have some.
for any m which is little o of log n, you will not have 1. So the threshold for being
Exponentially many.
you will have exponentially many. For m constant. If it's super constant, then I'm not sure. It will be super polynomial, but I'm not sure.
Times 10 all the time.
Right, m.
Sure.
The average degree is constant. When we say constant, it means the average degree is constant, not the number of edges. Yes, of course. So in this work, we consider the uniform distribution. However, we will not abandon the planted one, as one of the techniques to analyze the uniform distribution will go through the planted distribution. So our results are basically to characterize this distribution. So what's the main difficulty with this distribution as opposed to this one? So this is actually GNP, right? So you exclude some edges, but then so another possibility to define the planted model is to take every edge that respects the coloring with probability p. Okay, so you have either m edges or every edge with probability p, and the same game as in GNP versus GNM.
I see, yeah, and you throw out the ones as
So you give them probability 0. Just you include. So all the techniques, the spectral analysis, and all the techniques that were known for GNP basically carry on to the planted model as well. But if you consider the uniform distribution, then the edges are dependent. So the basic thing that underlies most analysis up to date, I think, is the fact that the edges are independent, or there is very little dependency like in GNM. And here it breaks down. So the edges are dependent, and it makes the analysis much more complicated. So we characterize this. So having said this is not a trivial thing because of the inherent complexity of the analysis. And we do it for, as I said, for graphs where the average degree would be some constant above the threshold. And if this was the picture, the conjectured picture below the threshold, we prove that random k-colorable graphs with average degree above the threshold have this structure. So, and this we show rigorously. So there is only a single cluster of proper k-colorings. So you would think of the average degree as constant. And the size of the cluster is exponential in n. So if m is not constant, then this is not true. But for a constant n, the size is exponential in n. And almost all vertices, and this reads, this is a constant, but which goes to 0 as the average degree goes to infinity exponentially fast. But this is still constant when the average degree is constant. So all but a really small linear fraction of the vertices are frozen. Namely, they will appear in the same color classes all the time.
So what you're saying kind of is that if you look at the ensemble restricted to the k-colorable ones, it's going to look kind of like your planted solution and
Right.
little things around it.
Right. So this is what we actually prove.
Okay.
What is frozen?
We say that a vertex is frozen so you cannot say that a vertex always takes the same color, right? Because you can always permute. So you can think of a set of vertices as frozen if they always appear in the same color class. In all the colorings, all these vertices go along in the same color class. And if a vertex is such that it has this property, then we say that it's frozen. And basically what this implies is that the planted and the uniform model are basically alike, which was maybe what one would think to begin with, but then is not sure how to go about and prove it.
So you will make this more precise?
Yeah,
next,
sure.
Okay.
And next.
Where it's not precise enough?
No.
Well, it doesn't define what a cluster is.
Yeah. So yeah, I'll show the result, and then I'll show what are the constants in the clusters. But the way to think about it, so this will also be the diameter of the cluster, the exponential decaying in the average degree times n. This will be the largest distance between any two k colorings, and the size of the cluster is e to this number. So it's exponential in n, but the coefficient, the constant is also going to 0, or is the degree. So all of this will become more formal. So this is just to give the flavor of the result and how it relates.
Now, can I think of walking in the cluster with short distances?
Yeah.
Yes. So this is what it means. So,
well, you said the diameter is sort of, you told us about the diameter, but the question is, can you go with steps of constant distance?
Of logarithmic. So
logarithmic unit, okay.
Okay, so this was characterizing how the distribution looks like, and this also enables us to claim that there exists a polynomial time algorithm that indeed finds some proper k coloring when the density of edges is sufficiently large. And so maybe it's nice to think that we rigorously complement so we maybe we suggest or support the following thesis. So when the clustering is simple, the problem is easy. This is what we prove. Okay, so you have a single cluster, and then you have this nice polynomial time algorithm that solves it. When the clustering is complicated, then the problem is harder.
Do you prove that?
No. So.
Oh, okay. There's your
So, but in particular, people did suggest at some point that maybe you could plan solutions in k-set to make it sort of a hard problem to find that. Did you say that?
Yeah, it depends on the structure. So what I'm saying that it doesn't depend if the.
He's saying something different. He's saying that the way that it is k-colorable in the unsatisfiable regime is that it looks like a planted solution, but not that planting a solution makes it easy. I mean, the converse.
That it has a single cluster. So maybe this is. So we are not. This is not something rigorous, but we are saying that maybe.
No, but the first one is rigorous.
Right. So this is rigorous. We show that. So this is also maybe, it's not a causality. Like we don't show that whenever there is one cluster you can find it, a solution. But we say that it might be that our results suggest that when the clustering is easy and nice and you have this one cluster, then it leaves enough imprints in the
but
graph.
In just what you proved that finding this planted coloring is actually polynomial.
Not planted, but there is no planted coloring. But finding.
They show that when they restrict, when they put that conditioning on, it's essentially equivalent to planting a color.
Planted was already shown in the 90s.
Right.
Right.
That it's easy.
That it's easy. And we show that this is also easy.
So you show this is the only way that you get that. Generic. I mean.
So was that also
But it doesn't say like when I'm below threshold, okay? And my problem has not yet broken up into clusters, so I've got this uniform thing. I mean, I'm being that little guy again, okay? You would like to prove that it's always easy.
just above
Yeah,
the
but it
threshold.
would be via completely different techniques.
Right,
Way
so
above.
yours
Right,
doesn't
constant.
suggest any
No.
proof of that. It's kind of for a different reason.
Right.
Okay,
So-
that's fine.
Yeah, the techniques that you are using are completely different.
Is there a belief about what happens just above the threshold?
Come again?
So this proves that far above the threshold,
Constant far.
yes, but still.
Constant
So
factor.
what if what if the threshold is at 5 point whatever, and you go at 5 point whatever plus 0.1?
How does it look like?
Is it believed to be hard, or is it supposed to be a single cluster?
Must be hard.
So there I think there might be a separation. It is possible that you have one big cluster, but then these algorithms for sure fail for it. So as they are stated now, they will fail because they are not, so they don't have this granularity to work with such sparse instances.
Although when you look back
But,
at
uh,
like
It should not be clustered. It should not
Or-
be cluster. There should be right above the threshold. And think of something that right below the threshold you still could color, and then you added a few extra, a few extra edges. So you have so intuitively this is again this. You could think of adding those few extra edges but you're restricted only to add them between things that already have a different color. So that model should, very close above the threshold should be close to picking a uniform k-colorable, and then you will maintain the clustering picture you had from right below the threshold. I think that's what one would believe happens right above the threshold.
So it's interesting to see when so
I wasn't totally convinced.
because here you have one cluster, so why should there be any phase transition from right above?
no,
But somewhere
what
it should
he's saying
cross.
Is that
Do you expect some transition to occur, like the physicists say there's some non-analyticity when you go when you're below threshold and you go from one cluster to it breaking up? What he's saying is then you would have to have some non-analyticity coming from there when it goes from many clusters to one cluster. And
So why should this
that's what you
happen? At some
expect by duality, that conditioning, there should be a mirror image of the picture you see below the threshold, where you have several transition points. You should see something like that also above.
well, if you think about
That could
GNP, the simplest things about GNP, they certainly are proved via this
Duality.
a duality, a mirroring of the thing. So
yeah, so this could be also
nevertheless, it's still, even if it's still supposed to be hard, it's just hard for a different.
No, then it should be by duality also be easy, because you could use belief propagation above to search through these clusters.
What
If you're way above.
connectivity
If you're
threshold?
way above.
No.
Condition on
If you're just below, belief propagation, survey propagation should work.
Right.
So therefore, just above by your non-rigorous
If
duality
you're just
argument,
above, but you condition on it being k-color.
yes, then again it
Right.
might be your survey
Well,
propagation.
maybe survey propagation would still work, but we don't really know whether survey propagation
And then
works
way
all the way
above,
to
it's
the-
also easy. So you're telling me that random k-set is by your heuristic easy.
Well, near the threshold, there's no proof it's easy, and survey propagation seems to work well for small k close to the threshold, right? For k equal, more substantial k equals 15, we have no idea how survey propagation works. So this is very special to sparse. So all this clustering picture is only established for a larger k.
Okay, so coming to the to the title of the talk. So what we actually established that almost all k-colorable graphs are easy. So for every given density greater than some constant. So just to put it in a framework, so what was known so far, so we have the planted versus the uniform. So below the threshold we had the clustering and the survey propagation. Above it, so we had Alon and Kahala's algorithm. This is the algorithm that was proved in 1997 to work for the planted k-coloring, planted k-colorability distribution, which we show that also works for the uniform case. So what we show is that there is a similar clustering phenomena, but only one cluster. When you go a constant above the threshold, the planted and uniform distributions are close in the sense that the structural properties that interest us are basically the same. And we show that Alon and Kala's algorithm also works for the uniform distribution. And if you go a large constant times log n, then the planted and the uniform coincide. And this is not hard to see because if you have only one, so in the planted, you can prove that you, with high probability, have only one coloring. And then how does the planted work? It says choose the planted coloring, but if it's only one, then it's uniform. Every graph will have the same, basically the same probability. And then everything becomes trivial.
Essentially everything is frozen when you do it.
Right, everything is problem, and this regime is let's say,
I see, and that's
very
your
easy.
1 minus e to whatever. When you go up that high, then
It
that
will be
factor goes to 0.
e to the something that goes to 0, and then it's 1 for the planted plus little o.
Well, there's one thing which is actually sort of astonishing, right? Because in k set, we sort of, well, okay. So
The next slide is case set, so maybe I'll just flip.
Okay.
So in case set,
See, now I'm sort of slightly confused because Ansys proves that for Beam and others that k set is
In
actually
Descartes.
supposed to be difficult.
Of course it is.
Right,
Yes,
this is
so-
not conditioned on
Reputation algorithms,
This talks
right?
about only
okay, so this is sat. So this is you take k sat above the threshold and restrict yourself only to satisfiable formulas.
And the same thing is true of the last one too. If you flip back to
Right.
k-colorings, they put themselves in a very in a set that's tending to measure 0 of the configuration.
No, that's not, yes.
It's the same thing here.
Yeah,
It's
this
the
is
same thing here.
yes. So if you go below, so this is what was known
Not at all.
in the uniform case.
And one would expect for the analog of a refutation type thing to have something like beam, carpet, etc. for the coloring, wouldn't you? That if you didn't look at the ones that actually are colorable and you went above threshold, it should be hard.
hard to prove that it's not.
Yeah, that's it.
Yeah,
Right.
that should be hard.
Hard to prove that it's not colorable. I mean, you've not that there is an analog, but one surely expects an
Okay, so
analog.
what they prove is that a particular algorithm does not work. That's what they
Well,
prove.
they proved a particular class.
Yeah,
of
which is a limited
algorithms.
class. We know algorithms which are better that do work. I mean, at the densities that their algorithms do not.
I see.
That doesn't
Okay.
So, but but in general, it's still, the case of proving non-satisfiability or non-colorability is much more open, and we know much less.
So for the planted models, if you take density, some high enough constant, so AB's algorithm from 03 settles the problem for the planted case. And there is another non-spectral work of me and Uri, similar to it's a k-opt version for SAT, which also solves the planted setting. And what we show by showing that the planted and uniform are close is that both algorithms and generally speaking, every algorithm, I think, that was shown to work for the planted distribution will work for the uniform case as well. And in the SAT case, so things become even easier when you cross the log n threshold. So then just the majority vote gives you everything with high probability. Ben Sasson, Bilou, and Gutfreund. So they had this manuscript showing that the majority vote works with high probability for the uniform distribution. So what was known up until now was an exponential time algorithm, of course running not in 2 to the n, but some 1 plus epsilon to the n due to Chen. And one of the open questions was, what can one do in the uniform stat distribution? So this was like an open question, and we kind of settled it, showing that whatever is known for the planted is basically known for the uniform case as well.
As long as CK above this large constant.
Yes, above this large constant, right. So also all the planted work are for a large constant. So for neither of the planted or uniform, anything is known when the constant is arbitrary, say 10. So I don't know any work that proves rigorously anything, at least. I don't know. Okay, so what is Alon and Kahala's algorithm? So I'll run through it fast because time is. So the basic algorithm is you get an approximation of some proper 3 coloring. This is done via spectral techniques. And analyzing spectral techniques in the uniform case is really a big hassle, and it's lots of technical work because all the nice things, the results that are known for GNP, all the discrepancy properties, you have to reprove them, and things are of course dependent. So this was the main. So the main work here was technical and not in the algorithmic sense. So it was more in the analytical sense. So the first step is to get some approximation of a proper 3 coloring. Then there are 2 phases where you basically you're basically left with a partial coloring, but typically with high probability it will be correct. That is, it is part of some legal 3 coloring. Okay, so you are doing this combinatorial local fine-tuning, and then you are left with something that is partial. The graph is not colored yet, but you know that you can extend it. And luckily, so enough vertices are colored so that the graph induced by the non-colored vertices is easy. That is, the connected components are logarithmic, and you can just exhaustively search it. This is their algorithm.
So what's the suspicious vertex?
So suppose that in the approximation you have very few edges to the other color classes. Then you cannot be sure that indeed you should be. Let's say you have 1 edge green and 1 edge blue. Can you say that you're red? If you have 100 of these and of these, then your security level. So, and similar stuff to this. So
But you only do it once, right? You don't go.
So it is
You
iterative.
don't have levels of suspicion.
No.
Okay.
No, it's an iterative process.
It's an
It is
yeah.
iterative.
It's
So you do first pull off the most secure ones,
right.
and then you have kind of
So
levels.
the other way around. You
Okay, or
remove
the
the
other-
most suspicious one,
You
and
remove-
this
Yeah.
makes other ones
Suspicious.
so you
Yes.
remove
If your neighborhood is suspicious, then you're suspicious.
So
Yes,
when
so
you
you-
want to analyze that, how do you avoid that you reuse randomness and lose independence?
So the way to analyze it, which is another talk, is to assert certain properties that a graph has. Okay, it has these properties. Given the fact that it has these properties, the analysis goes through. You don't analyze each step using fresh randomness. You just assert, okay, I say that a graph is typical if it has A, B, and C. Then you show that if it has A, B, and C. So maybe I'll show a similar argument depending. So, okay, so maybe I'll flip through this. Or are you interested in hearing?
Yeah, we are.
Yeah. Okay.
I don't know if other people. I'm okay with that. I'm having.
It's
I'm
3
learning
slides.
something.
Until 8.
I have a lot of. I didn't sleep till late. I slept till 6:30.
Okay, so how does our result contribute to SAT and message passing? So warning propagation, you can think of it as the first introductory algorithm, toy problem to message passing, but still. So what's message passing? You have this bipartite graph. On the one side, you have think of a 3CNF. On the one side, you have the variables. On the other side, you have the clauses. And you have an edge between a variable and a clause if it appears in that clause. And basically, the messages go between variables and clauses and the other way around, and they convey some information. Hopefully, it all converges. Either it's warning propagation, belief propagation, or survey propagation, and you can extract some useful information from this. So what are the 2 kinds of messages in the warning propagation? So 1 is a clause to a variable, which can be either 1 or 0. 1 is a warning, and 0 is you're okay. So when does a clause issue a warning to a variable x? If the other two, so let's say that the clause is x or y or z, this is like the polarity. So if y and z told c that they are negative, that is, they are tending to take false, then c immediately needs x to be the satisfying literal. So c issues a warning to x, telling him, I want you to be the satisfying literal. If both of them send that they are going to falsify c. And x in return tells the clause some kind of a majority vote. So it considers how many clauses where it appears positively sent a warning versus how many negative where it appears negatively sent a warning. And you can think of just the sign of the difference. It's either -1, 0, or 1. Okay, 0 is undecided, 1 is tending to true, and -1 is tending to false. So these are the two messages that are involved in the warning propagation.
Wait, why does it send it to a clause?
Yeah, so it doesn't take into account, this is the cavity thing, it doesn't take into account.
So that's the only way how it knows that. I mean, it just not taking into account the clause and then it sends it to the
Right.
clause. Okay.
So the warning propagation is the following algorithm. You initialize all the messages to 0 or 1 with probability half. So this is one way to run it. And you repeat until there are no changes. You randomly order the edges of the factor graph, and you evaluate all messages. So this is so you can do it also just evaluating the edges in parallel. Clause to variable, then variable to clause to variable, and then you don't need this part. But then, so it's a different algorithm, and so this is the way like the book puts it, and you can also show that this has. So in some cases, the other one may get stuck, and this can overcome it with positive probability.
So are you saying this one is always better than the parallel one, that the sequential one is always
Yes,
better than the
I
parallel?
think that you can claim this. So, and at the end, you just calculate how many warnings you got from positive to negative, and then this is your assignment.
Mm-hmm.
So actually what Uri, F is Uri, M is Elchanan Mosel, and me showed on my previous visit here that this algorithm, if you run it on planted instances with constant high density, then it's useful in the following sense. It converges after log n iterations. And for all but such a small number of variables, it coincides with some satisfying assignment. And the unassigned variables are, again, easy. They break into
So
these.
they're a little piece
Yes.
of log or less.
Right. And then you can complete.
And none is assigned wrongly.
Right. So either if you are assigned by this procedure, then it's right in the sense that it coincides consistently with some satisfying assignment. So if you look at maybe a better way to state it, if you look at the variables that are assigned by this procedure, then their assignment is part of some satisfying assignment of the formula.
That's the zero.
Yes. And
There exists a satisfying assignment such that they all agree, and the unsatisfied pieces are so little that they can then take care of it.
the unassigned pieces. Maybe it satisfies everything, which is probably not the case in the planted, but still you can take care of them using exhaustive search. So how does this relate to everything that was said up until now? So our work also implies that this warning propagation algorithm works for uniform SAT. Mm-hmm. And so reinforces maybe the following thesis. When the clustering is complicated, then survey propagation is known to work. When the clustering is simple, then the naive warning propagation already works.
So instead of calling that BP, belief propagation, you call it warning propagation.
It's different. BP involves probabilities, and it's this is discrete. This is the discretized belief propagation.
I see. So this is really simple. Yeah.
Right.
Okay, good.
So this is
Good.
why naive is maybe appropriate.
Okay.
So you wouldn't expect it to work for
So
real life.
That's why you have to be much further into the.
Or this is why we can analyze it rigorously. So sometimes there's a difference between what's right and what you can analyze rigorously.
Now this also works below the threshold, right?
Warning propagation? No.
No?
Because it's so sparse that everything immediately is don't care. So it's discrete and it's sparse. And
So
this
it's not
doesn't go.
belief, it's really, but it's just because the nature of the solutions which are colorable or satisfiable in the uncolorable or unsatisfiable regime are really different from the generic. And they have a structure that's so different that warning propagation works on.
No. For low degrees, you also should just have one cluster.
No. So it's. So what happens when you look, let's say it's very, very sparse, let's say like a graph.
3 set for 1 or something.
Yeah. So in these cases, kind of, it really doesn't care because kind of it's so easy to satisfy it. It doesn't give any recommendation. This kind of gives you a
Then random
recommendation.
works. I see. So in the other case, it doesn't give any recommendation, and random will just work.
Except when you run into a direct contradiction, when a variable is set for you, you set it as, when you get to a clause which is with one variable left, you set that variable like what it has to be.
Right.
So that will work very, very well. But what is CK? What's the best estimate? So, because
Maybe 100 or. So you have to run through the calculation. It
How
not
does it depend on, so.
What's the K
SAT, how does it
dependency?
depend on K?
for the coloring, it's K. It should be K to the power of 2, like in Alon and Kahala. So it's K to the 2.
And for SAT?
For SAT, then it's a different story. I think, yeah, I think it's exponential. Even worse, maybe K
Who cares
factorial.
because he's done
Oh.
like that.
That's right. So the threshold there is at 2 to the K log 2, and the threshold for somehow things being for the easy algorithms to work below, so it's 2 to the K log 2 to the K over K. So if you're below suitable constant 2 to the K over K, then just setting everything at random works. And the question is, what is the, will this be K times 2 to the K?
I think K factorial, but because
Well, that's the bound, right? So that's much
no, but
larger
I
than
think that this is what it also will take, because you have this certain type of clauses where there is only one satisfied literal, and they are only 1 over 2 to the K, 1 over 2 to the K, not K factorial. So there's a certain, at least as the analysis goes, you are.
No, I think
what was the multiple?
Maybe
of
the
2 to the
question,
K?
yeah, the question was.
What
so
was
the
the
constant is at least 2 to the K because below that it's not satisfiable. It
Below
is
that it's
satisfiable
right.
anyway. It's asking is 2 to the
Oh.
K times what?
I think 100. It should be something. So at least for the at least.
So you think that the fixed constant times 2 to the K will be enough?
I'm not sure. I'll have to run through the arguments again, but I think that.
So the K dependence is interesting.
So in the coloring, it's for sure K squared. In SAT, I think it is some constant times 2 to the K, because I think it should be some constant. Right, AB also can contribute to the.
So you're really asking what's the result in the planted case, because you say the planted case
Right.
really the results
Right,
transfer to this
right,
case.
so just look at numbers.
So
AB's.
So for SAT it's AB's work, but you
Oh, for SAT
only
it's
on
AB's work,
3
sorry.
SAT or did you
I
do
only did
KSAT?
3 SAT.
Yes, I'm not
But
sure
there's some details that you
No,
have
but
to
you
add
can-
to do KSAT.
You can generalize it and then look like if what makes sense. I'm not sure. I think it's a constant.
So, I mean, the way I did it, it would have to be at least K times 2 to the K. But I did it in a really sloppy way. It can definitely be improved. What do you get when you improve it? I don't know.
My guess is you'll improve the constant that multiplies the K 2 to the K. It's interesting.
It's
to
possible.
He had to work very hard in another case to get rid of that
No, I
case.
think it's duality. He thinks
Yeah, I
the
think it's duality. So I think that
1 over K
we
becomes
know
K.
that improving the simple algorithms for that do to the k
Right.
over k. If you do small improvement, all the improvements which keep the same general type of algorithm, they only improve the constant that multiplies the 2 to the k over k. So based on that kind of heuristic duality, that would be my guess. But it's interesting to see.
So even the Greek algorithms? I mean,
What?
The Greek,
The
the
Greek-
Carusis, the 3Ks,
I mean, all these algorithms
the
make,
non-myopic.
right, all these algorithms make a lot of sense for small k. For large k, you're way off from the threshold. You're at 2 to the k over k, and it improves the constant
also the non-myopic, it doesn't only helps with the
constant that multiplies the 2 to the k over k. Yeah.
Okay, so how much time is left? 10 minutes.
Danny, I'm having
Okay.
fun. I'll stay here forever. But when are they allowed to leave? So when could you reach a
No,
nice point?
Now,
When could you reach
this
a
is
nice? No, well, I mean, kind of.
no. I'm saying now it's the technical part, which is how to prove.
Should we thank Danny, and then those of us who want to see more, see more? Does that sound reasonable?
For me, it's
Yeah? Okay, let's thank Danny.
yeah.
Okay.
Okay, so we have the uniform distribution, and the difficulty is the dependency. So for starters, let's consider the planted distribution and see how we can work from them. So the basic notion in the analysis is a notion of a core. So we are now in the planted setting.
Children's sick, but this is being.
It's being taped. So in the planted so let's go one step back to the planted setting or aside. And so every vertex is expected to have let's say that D is n times p. So every vertex is expected to have D over 3 neighbors in every other color class, right? And D is some sufficiently large constant. Now, let's say that you believe for these two claims. What do they say? With high probability, you don't have a small graph, small meaning less than, let's say, n over 1,000 vertices, but the average degree is, let's say, 1,000 times more than what you'd expect. So you don't have these small graphs with very large, unexpectedly high average degree. So this is really standard first moment calculation in random graph.
That the edge distribution is not tremendously non-uniform.
Right. So this is, you will believe. And the second claim says that in the planted setting, you do not expect to find proper colorings which are very far from the planted one. And why is this? Because let's take two colorings, let's permute them, then you have this independent set in the places where it breaks, and it's of size linear in n, and there should have been edges with probability p there, and in G and P you don't expect a linear size independent set. So these two properties are really, so you have to work it out, but you can prove it.
Like there's some boundaries
On the core, right. So
these 4 letters are not defined.
Core. He's saying that you didn't define.
right, okay, so maybe just ignore it because it's on, so you don't have, so I'll define in a second, so this claim just reads that you don't have two proper, so all the colorings are close to the planted one. So to begin with, we have this cluster in the planted setting, but not the constant that we would like to have. So what does these two claims already give us? So suppose indeed that every vertex has the expected degree, D over 3 in every other color class, and the two claims hold. Then I say that G is uniquely 3 colorable.
So when you say expected degree, so the expected degree to color classes, so to its own color class
is 0, right. So you have this vertex V here, and it has n over 3 possible neighbors in every other color class. Each neighbor is picked with probability p. So this is the expected degree that a vertex V will have in every other color class.
I see. And then you're going to show that.
So suppose this is the
things are
case.
gonna have close. Most things are going to have close, but obviously you're going
Okay, so I say that G is uniquely 3 colorable, and so this is just a flavor of one proof also in the flavor of Alon and Kahala and all the analysis that goes around in the planted setting. So suppose that this is not the case, and you have a proper K coloring which is closed, okay, so suppose that you have a proper K coloring and it should be closed, right, by claim 1. Okay, so if it is not phi, if it is not the planted one, then let's consider some vertex on which they disagree. So they should disagree on all d/3 neighbors in that color class, right, since this is a proper coloring. So what have we? We have a small, so let U be the set of disagreeing vertices. We have a small set, and the degree is high, the average degree is high, and this contradicts the lemma. So if indeed, so what's not going to happen in this picture is that every vertex has the expected degree if P is constant over N. If the average degree is constant, then of course you will have vertices with 0 degree or with very high degree. So this is indeed the case with high probability for average degree which is constant time log n, and this gives you the proof of uniqueness of the coloring. And when the average degree is constant, this will not happen. But the core captures the notion of these frozen. So these are the frozen variables, right? If you have a unique coloring, these variables or vertices are frozen. And the core indeed captures this property. So let's define a core to be the set of vertices that comply with this property. They have at least not d/3, you need some slackness for the proof. Let's say d/4 neighbors, that they are also part of the core. And this is for the algorithmic part, that you don't have too many vertices outside the core. So for the algorithm, they may influence you. And one can prove using rather standard probabilistic calculation that you have a core which is big. This gives you the size of the cluster. So the freedom is at most whatever left outside of the cluster. And the core is uniquely 3-colorable, and what's left outside the core is this logarithmic size connected components. So this is in the planted case. So now,
do we here also see that the core is log n connected?
So what do you mean by log n connected?
Not the core. The core is a unique set.
The core has
a subset of the graph. The core is a subset of the graph which has
Which
unique
has
coloring.
these properties.
There's a unique coloring, so it cannot move to any other coloring because there is no
There's a
other
unique-
coloring.
These are the frozen
Right.
variables.
Oh, I see it now. If
The
you
core
extend-
is the frozen variable.
right. The core is the frozen variable.
This
This,
the cluster of the.
And so he's telling you the core is pretty damn big, and that's the estimate on
So
its
now
size.
if you, and the other small components, so each one of them you can always recolor it completely.
Sure.
If it has two coloring, but it's so small, so we changed only a small number, the color of a small number of vertices. So you can move from one coloring to another by changing a small number of
Oh, by small as these.
Because these are only log n.
like the
It
size
has
of the
that.
largest connected component outside the core.
Right.
okay, so this is the picture in the planted case, and we're interested in the uniform case. So this is one technique that we use in the proof. So consider some bad graph property, and let mu be the expected number of proper k colorings of a random graph in the uniform distribution. Then what we prove is that the probability that the probability of A, think of it as a bad graph property. There is no big core. There are small graphs with very large number of edges, some bad property that you don't want to have. So the probability under the uniform distribution of this bad property multiplies by at most mu times the probability it was in the planted setting.
This has nothing to do with the property being bad. It's just a general.
Right.
Right.
Of course, but if the probability is good, then this gives you,
Yeah.
Yeah.
You have to apply it for bad events.
Right.
Inequality is just a general.
right, if you're thinking analysis-wise, then right, of course. So, and mu is exponential in n. So the number of colorings is exponential in n, so you have to be, so this technique will not give you all the way. So there is another bunch of slides. So, and why should you believe it? So typically a graph, so in the uniform distribution, typically the graphs have mu satisfying assignment. Okay, so let's say that all graphs have exactly mu satisfying assignment. Then how do you pick a graph in the random? You pick an assignment, you pick a proper k coloring, and then a graph. But then the graph, so you have at most mu ways to pick each graph, one per each coloring, and then it's some kind of union bound. So this is just hand waving, but I think it's plausible to believe this bound. So let's see how we can apply this to prove that also in the uniform case you have big cores. So let A be the bad property. So regardless of the proper k coloring, you will not get a core. This is the bad property. So in the planted, you can show that the probability of such an event is exponentially small in n, and mu is also exponentially large in n. But so the probability of not having
exponentially
large,
small constant.
right? So
Fine. Good.
So you can always mess around with how big the core should be or how small, and you can get that C2 is bigger than C1, and then if you multiply them both, it goes to 0. Okay, so to analyze the algorithm, so we need the fact that we have a big core, but we need two more facts. We need the fact that there are no small and dense subgraphs. Mm-hmm. And we need the fact that outside the core, the components are logarithmic of size. The problem is that both properties don't hold with such a magnificent probability, only with probability which is 1 over poly. And then you cannot use this union bound technique, and you have to directly analyze the uniform distribution, which is a big pain because of the dependency.
So union bound, Lover's local lemma is not good enough either.
So I must admit that I haven't checked it, but
It's kind
my
of
guess
designed,
that
but the reason he's asking is because Lovaas designed the Lovaas local lemma for these situations. Kind of. Well, I mean, Danny may not, or he may. I mean, Danny's a student.
No, but
Right.
it's not so clear that the events are independent. So you have the dependency graph, but almost everything depends on everything else.
But I think in the Lover's local lemma, in the sort of final version, whatever, it could even be the complete graph, the dependency graph, if the dependencies are weak. Because you measure the dependencies.
okay, so here is an
So we should
alternative
look at
way. If you
We
don't
should-
want,
it might give a nicer, an easier proof, because I'm sure that that's painful.
right? So it's just some heuristic how you can analyze things when things are dependent, when the underlying events are dependent, and you don't want or know how to quantify the dependency.
Mm-hmm.
So this is basically a counting argument, and the question is if I'll have time to show it. Okay, maybe I'll run through it really quickly in like 5 or 6 minutes. Or should I stop? Or
Should we give you another round?
Yeah, okay, so
everybody can leave?
basically, I'll just say one word about
No,
it.
I'd like to see it. I don't want to hold everybody else here. I mean, like when I go to lunch, people don't leave
Yeah.
till I finish eating. When I want to watch somebody.
So I think maybe
Anybody who doesn't want to watch should leave.
it's technical, so maybe we can just
I
there.
wanna see it.
Yeah.
New part.
Yeah, this is
This is where it starts to be new.
Exactly.
right. So
I
this is
wanna
the
see it.
interesting part. So maybe. Okay, so how does it go? So let's try to prove this claim. So with high probability, you don't have small subgraphs with too many edges. So we think of M as C times N, and the proof technique is union bound, but the normal union bound. Let's fix a set U of T vertices, T is small, and fix a bad graph on these vertices. And so what we have to do is just upper bound the probability of such a bad graph, and then take the sum over all bad graphs U and over all possible T's. So this is the interesting case. So this is just the union bound. And then the question is, what is the probability that a fixed bad subgraph appears in G? So if it was G and P, it was just P to the time of the number of edges, right? The edges are independent.
What's the matter here? It's that there's a size T subset that has
this number dt over 10 edges spanned by this subset.
That was violating claim 1.
Right.
The dt over 10 came from violating claim 1.
There are too many
Claim 1
edges.
had a dt over 10.
Too many edges in spanned by a small group.
okay.
So this was the answer if it was the G and P. And okay, in the uniform distribution, we don't even have a P. So let's define M, the number of edges, as the expected. So if you take the planted model with all the partitions of the same size, then you get that the number of expected edges is just this one, because you have to choose the two color classes, 2 over 3, and then the complete bipartite graph. This is the total number of edges times P. Yeah. Okay, and P is.
What did you say?
This is what I said in words. The expected number of edges.
Okay.
Had the graph been planted. And P is 3m over n squared. So what we shall prove that the probability of a fixed subgraph with R edges is at most 6 times P over R. So 6 is not sacred to the R. You can have instead of 6. So it should be 1.
Well, yeah.
Right? Intuitively, you think that if you condition on k-colorability and compare it to the planted, then maybe you expect it to have less edges than the planted case. Maybe. Okay, so definitely 6 is, so you can get 1 plus epsilon if it really matters. But for this case, 6 is just fine. So if we did it, then this is the union bound. You choose the vertices of the bad graph, you choose the edges of the bad graph, and you multiply times, so this should be D, the C is D. And you multiply times the probability that all the edges are indeed present, which this claim gives us, and then you just do the regular binomial coefficient stuff and get little o of 1. So this is what's new about.
So this is your C1 and C2, basically, that C2 is bigger than C1.
So this is not the C1 and C2. So the union bound was.
Oh, this is the U.
This is like directly analyzing the uniform distribution. Okay, so this is our goal, to prove that under the uniform distribution, the probability of a fixed graph with R edges is at most 6p to the power of R. So let's fix the bad graph B and consider this bipartite graph, auxiliary graph. On the one hand, we have all the B bad graphs, the graphs that contain B. On the left-hand side, we have all k-colorable graphs with M edges. And we want to show that this number is little o of 1, or this time. So the fraction of these bad graphs is at most 6p to the power of R out of all possible graphs. So the way we do it, so on the left-hand side, we show that the average degree of a graph in the. So I still didn't tell you how I'm going to connect the edges. But once I told you how I'm going to do it, it will turn out that the average degree of a graph in the left-hand side will be delta 1. On the right-hand side, it will be delta 2. And double counting gives you that these two properties are equal, right? It's a bipartite graph. But we will have this nice property. The delta 2 over delta 1 will be at most 6p over R. So I'm going to show you a way to construct this graph. It will be a procedure. I connect a graph G1, GI to a graph HJ if I will tell the procedure, the magic procedure in a second, but if you take G1, you apply the procedure. It is non-deterministic. It can give as an output let's say, delta 1 graph, at most such number of graphs, and you put all the edges. Okay, this is the way how I construct the graph. So you take a graph here, you apply, I'll just say the procedure. So you take a graph which is B bad. You rip out all the edges of B, and you redistribute these edges amongst all the other edges so that at least one K coloring is respected. So you take a graph here, it is B bad, you take out B edges, and then you can get many graphs here because, what we want is to have many graphs, a large degree here and a small degree here, right? This will give us the fact that delta 2 over delta 1 is small if the delta 1 is large. So you take a graph, and you have many ways to get a graph here, just redistributing the edges. So if B is the total number of edges, then delta 1 is at least, you have to choose out of, so M edges are taken, right? You cannot use them. But you have this number of left edges, so take one coloring. So here I'm a bit cheating because the coloring is not in particular balanced. It shouldn't be balanced, but you can also show that this is the case with high probability. So separately you show that with high probability, for all graphs there exists at least one almost balanced coloring. So this thing you can show, and combinatorially from convexity arguments, so most colorings looks like this when it's balanced. So you have this number of total edges crossing here. You used only M, and now you have to redistribute the R edges of the graph between B minus M edges. And B is in the order of n squared, so this gives you just this number. And how many ways do you have to reconstruct? So suppose you're given a graph here. How many ways do you have to reconstruct a graph here? So you can guess which R edges were added. So you have M edges, right? Here all the graphs have at most M edges. You just have to guess which R of the M edges you redistributed, and then you have exactly one way to set them, because B is fixed.
I thought there were B bad ones. R.
So yeah, maybe it's a poor notation. So R is the size of B.
Oh, okay, fine.
And
fine.
B is the size of,
okay, that's
yeah,
fine,
it's
that's
poor
fine.
notation.
Okay.
So you have to just to choose the R edges that you redistributed, and then once you chose them, B is fixed. You know how to plug them back to G1. So this gives delta 2 at most R over M. And if you do the math, so it just comes out.
And you say that if you were really careful, you could get 1 plus epsilon.
Yeah, maybe. So maybe 2. I'm not sure. But yeah, you can reduce it. So if just one last sentence. So doing this is, let's say, pretty much standard. But proving that the logarithm, so we still have to prove that what's left is logarithmic. And this is really an obnoxious counting. So it uses basically the same technique, but it's really, so this is where Amin came to the work, and where who? Amin Khojaoglan, this is the first author. Okay. So he's really known for not fearing any technical obscenity or whatever, and he just crunched it to the bitter end. And so I think that maybe this is why the problem was left open for so long, because it's technical right to the bitter end. So this is why it took from 97 to 2007 just to close this bit.
So 97,
the journal, baby, 94.
The journal version for this is...
So this problem was open.
For 10 years.
Yeah, it's open for ages. And so yeah, even when Noga looked at it, he said, I'll do the planted thing. I'm not going to bother with the uniform case because it was so. Okay, but anyway. So that's it. Says thank you.